Just hold on. Yeah. Venkatesh, please start.
Okay, thanks.
Thanks.
Okay, so in this lecture, actually, we are going to see the Serre's theorem in Lie algebras. So it is actually like most important piece of information in the classification of semisimple Lie algebras, which actually kind of gives existence of a simple Lie algebra with a given Cartan matrix or the information about the Dynkin diagram. So, so this actually, I guess, Serre actually suggested this presentation, and then the proof that we are going to see actually appears in JTIC's paper. This is this IISc publications. So this is the reference. So this is actually the proof is kind of very fundamental. So because this proof actually carries to the theory of cost-moody algebra. So in some sense, the Serre presentation suggests what to like how to generalize things, and then to get some infinite dimensional examples. Okay, actually, as a joke, people used to say that the discovery of cost-moody algebra was started like some PhD project. Okay, so I will tell you why they were actually making the joke, because so you can actually see that Serre's theorem actually gives presentation of this semi-simple Lie algebras in terms of Chevalier generators. So you start with the Cartan matrix, and then you will be actually able to write down presentation. So the only thing that is involved in the presentation is the dimension of the matrix. Okay, that is n, which will be the rank of the Lie algebra or the dimension of the Cartan, and then you will have some relations. So in a minute, I will be writing down all of them. But then only input is this matrix. But if you start with the finite Dynkin diagram, this is indeed a positive definite matrix. Okay, so then you can ask this natural question. So you take Serre's presentation and then allow instead of positive definite matrix, some general integral matrix. So that will be called what generalized Cartan matrix. But then like it's basically a PhD project. Okay, so you understand its proof and then run through everything in that proof, and then with the assumption that A is a very general matrix. Then you see what you are getting. So more or less the story started like that. But again, when Gauss invented this Gauss-Moody algebras, so Moody actually kind of parallelly invented it from more algebraic point of view. But Gauss actually had lots of motivation from mathematical physics. So the affine Lie algebras actually has lots of applications in mathematical physics. So somehow it was so natural to consider this natural generalization of this semi-simple Lie algebras in the infinite dimensional analog. So and now I would say like so it's a most successful PhD project, because this actually kind of gave birth to this Gauss-Moody algebras and Porches Gauss-Moody algebras. So there are all kind of very important classes of Lie algebras. They find applications in almost all areas of mathematics. Okay, varying from number theory, combinatorics, geometry, and so on. Okay, so if in case if you want to pursue research in Lie algebras and related representation theory, so proof of Serre's theorem is somewhat very, very important. Okay, but it's a very long proof. Unfortunately, I have only 1.5 hours to talk about it. So I will just outline the proof. I will try to actually convey core ideas that are there, but like we will not be able to check each and every detail. Okay, so where the motivation comes from? So let's take SL2 example. Okay, so but SL2 is too small. But anyway, let's see what is happening there. Okay, so in SL2, so this is actually a three-dimensional algebra. So you have this standard basis x, h, and y. So this is the basis of SL2. So now, so you can write down relations with respect to this basis. So you have hx equal to 2x, hy equal to minus 2y, and then xy equal to h. So I'm not writing down all other trivial relations. So bracket z is 0 for all z in SL2. Okay. So you can ask now this question, okay, how do you actually come up with existence of some Lie algebras? Okay, so this is where actually one can use the notion of presentation. But again, like let's go with simple mind setting. Okay, so one way to do, like you can actually use what is called structure constants. So in case if I'm interested in proving existence of Lie algebra, so you know that the Lie algebra is uniquely determined by, so isomorphism classes of that particular Lie algebra is uniquely determined by its structure constants. So you can take basis of G, okay, let's call it xi, I range it from 1 to n. So then you can actually try to compute all possible brackets, okay. So because bracket is nothing but a bilinear form from G cross G to G. So in order to tell what is this bilinear form, it is enough to tell how this form acts on this basis elements. So then you will be having some constants like this. Okay, so these are called structure constants. And if you see Humphrey's book, in the very first chapter, he talks about structure constant, and then the structure constant must satisfy some properties. Okay, but then like if you are interested in some particular Lie algebra, let's say like we are interested in the existence of simple Lie algebras. So then what you do, like you can actually like work with the root system, and then you can try to determine all possible structure constants. Okay, so that is one approach, but again that is not very successful. So for example, let's take E6. So if you take E6, it's rank 6 root system. So you have the simple roots. From the simple roots, you can write down all possible other roots. So from there, like you try to understand how the Lie algebra actually should behave and so on, and then try to determine all possible structure constants. So most of the structure constants are actually already, you know, for example, so you have what is called this root space decomposition. So you can write G as H direct sum G alpha in phi. So now you have a very nice basis of G consisting of basis of H and this root vectors that comes from G alpha. Okay, so so this is more like a recall. So let's see how much we know already. So let's have like some basis. So let's call okay L as my rank. So my rank of the Lie algebra, which is the dimension of the carton. So then you have this basis of H. So if you remember, the Hi is defined using that. So identify H with H star. then alpha will correspond to something called T alpha, then you normalize. Okay, so H alpha defined to be 2T alpha divided by alpha alpha. Okay, so the T alpha corresponds to alpha in the identification of H with H star. So because the killing form is non-degenerate, so you can identify H with H star. So basically you take H and then send it to the killing form evaluated at H. So that is actually an isomerism. So given alpha in H star, so which is a root, then you have pre-image that you call it T alpha. So then you have this H alpha. So now if I take the simple roots to be alpha 1, etc., alpha L, the corresponding elements, I'm calling it as H1, etc., Hn. So now what else you know? So you also have like given alpha positive root. So you can pick X alpha inside G alpha and then Y alpha inside G minus alpha, so that the bracket of H alpha Y alpha becomes H alpha. So this triple X alpha, H alpha, Y alpha is indeed SL2 triple. So that means the subspace spanned by these three vectors will be isomorphic to SL2. So that means you have some already structure constant among this part of the basis elements. Okay, so let me just recall H alpha X alpha will be twice X alpha, H alpha Y alpha will be minus twice Y alpha, and X alpha Y alpha is H alpha. And this you have for all alpha in positive roots. So the negative root are included. That's already included. Okay, so something you know about these elements. So H1, etc., HL. This is a part of the basis of H. So this is the basis of H. And then if I take this X alpha, so this is basis of this union G alpha, alpha in phi plus. So this is the N plus part. And then you have Y alpha, alpha in phi minus in basis of G minus alpha. So you have all this standard basis consisting of basis of H and root vectors. So now this is actually kind of this formula tells some structure constants. So what if you go ahead? Okay. So if you take alpha beta in phi plus, suppose alpha plus beta is again a root, so it's supposed to be in phi plus. So then you know that the bracket G alpha, G beta must be equal to G alpha plus beta. So this is something we have already. So that means X alpha, X beta is, so you can actually like, so remember these X alphas are already chosen. Okay, so they are not something you are going to construct. So they are chosen so that this SL2 triple is actually made. Okay, so the choice of X alphas are made. So you have this X alpha beta, and then you need to have some constant here. Okay, so this is something happening in the side of N plus. Similarly, you can actually have these things for Y alpha, Y beta. Okay, and then you also need to see like how X alpha, Y beta they interact. Okay, so then you are getting some bunch of numbers. But then like it will be actually very hard to actually determine these things. Maybe like you can prove inductive, you can get unique structure constants. But if you use this to actually say the existence of simple algebras. I guess so. That is how like Cartan actually constructed. So he constructed each and every root system very explicitly, and then you have the structure constants. So that you have actually your simple algebras. But then this approach is not satisfactory because this is like going with very simple-minded procedure. Okay. So then you can ask like, so like, can we do something else? Okay. So why such question even arises? So if you think about it, okay. So you have this Lie algebra, which is okay, given, let's say, semisimple algebra. So then you can actually so you can use this algebra structure, okay, and then you can find nice generators for this. So which will be called like we will stick with what is called Chevalier generators. So as an algebra, of course, Lie algebra. So G is generated by Chevalier generators. Okay, so we will see in a minute what they are. So then one can actually ask this question like, so you have this very nice set of generators, and then can you use them to write down presentation? Okay, because you can talk about abstractly what is free algebra and then go modulo the ideal. So in particularly, there are relations. So you can talk about presentation of the algebra. And then you see whether that presentation somewhat uniquely determines your simple algebra. So that is the approach actually Serre suggested, and yeah, Titt's paper actually contains very detailed proof, and that proof is adopted in Roger Cartan. Okay, so that's where we are heading. So if we go back to SL2, as I said, it's two small example. So here already you have this basis, and then you have the structure constants. So it's a simple exercise to see that if you have a three-dimensional algebra with the structure constant, then it is uniquely determined. But now, what is the presentation? So presentation is also almost the same. So you take this Lie algebra. So now the only thing I can drop this h. Okay, so in the presentation. So this h, because it's being bracket of xy, I can drop it. So so it is generated by xy, and then with the relation, okay. Oh, yeah. So then I have to write. So you replace. So you replace this h by xy. Okay, in the relations. But the thing is, this is not the presentation that Serre is talking about. This is something small. But that is because this Cartan is indeed a small Cartan, one-dimensional. So we will be able to recover it by taking the bracket. But what is Serre presentation actually? Serre presentation is exactly this. So it is generated by three generators, x, h, y, and with these relations. Okay, it was generated by this and with this relation. And in order to prove, actually, it is exactly SL2, the most difficult part to understand that if you define such a Lie algebra, that must be finite dimensional. Okay, so here you need to prove it is exactly three-dimensional. So maybe like you should take it as exercise. So what is the exercise? Take the Lie algebra G, defined as follows, generated by x, h, y, and with the relations hx is 2x, hy is minus 2y. So if you take this Lie algebra abstractly defined, whatever. So yeah, if it is abstractly defined, then exercise is G is isomorphic. Okay, so let me not assume everyone knows what is the definition of this abstractly defined Lie algebra. So let me just make it precise. So we already talked about free Lie algebra. Okay, recall what is free Lie algebra. So free Lie algebra, it has some set of generators. Let's call it X to be non-empty set, which is a set of generators. Okay, so these are all the generators. So now we want to talk about the free Lie algebra generated by X. So what it is? So you take this Vx, which is the free vector space generated by X, okay, which is by definition direct sum of Cx, X in capital X. Okay, so now you have this TVX, which is again free associative algebra generated by X. So now you can treat this. So from here, okay, you can actually construct this TVX, so which is the Lie algebra coming from the common by defining this commutator as the bracket. So because this is associative algebra, by taking the commutator, you will have this Lie algebra. Then what is FL of X? FL of X. So sub Lie algebra generated by X inside bracket of TVX. Okay. So as I already told, TVX is actually huge Lie algebra because it will have monomial of the form x times y, but that x times y cannot be written as sum of Lie monomials. So that is the problem. So that is we need to take sub Lie algebra generated by X in this TVX. So this is what are called free Lie algebra. So now if we have free Lie algebra, then what is presentation of some G? So let's say G is given Lie algebra. So G is given Lie algebra. So then we say that G has this presentation. So we say G has the following presentation. So if okay, so what is the presentation? So let's say it's generated by some elements X, I, and I, and then with the relations, so R1, etc. Okay, it's not right. Finite relation, it's right. J, okay. So this Rj could be anything, like it can be like all some combination of monomials, Lie monomials and information. Okay, basically this is so this is a subset of FL of X. So broadly, that's what it is. So you say that if G is isomorphic to FL of X modulo, take the ideal generated by Rj. Okay, so then you call G is has this presentation. Of course, depending upon the generators that you choose, the presentation can vary. So it is important to actually come up with a nice presentation because So the presentation that you are writing should be useful, okay? And for example, when you are writing diagonal group, you always take that two important generators and then write down the presentation. Now, so why you choose those two generators? Because that's a natural generators that you are actually working with. Otherwise, like you can also choose some other generators and then write down different presentation, whether it is useful or not. Okay, so this is the definition of presentation. Now, let's actually like get to Serre presentation of Lie algebras. But before that, let me just motivate a bit. At least I will actually try to prove something about Serre presentation. So here is a fact. So I assume like all of you are like very familiar with the root system. Okay, I'm freely going to use all the notions that we know about root system. Maybe like to be consistent, I will just write down what I mean by the notation. So this is my simple system phi, which I denoted by alpha 1, etc., alpha L, and I denote this phi to be the root system, and phi plus or minus to be that positive and negative root systems. Okay, so this is these are all the notations that we'll be using. So the fact is, it's a simple exercise. Yeah, maybe we'll do it now. So given alpha in phi plus, you can always find. Okay, so let's say it is not simple root. Okay, so given alpha, there exists alpha I inside pi such that alpha minus alpha I is indeed positive root. So as a corollary, you can immediately see given any alpha in phi plus, alpha can be written as alpha 1 plus etc. plus some alpha I1 plus etc. alpha Ik, such that so the partial sum is positive for all or okay, so this maybe I'll leave it as exercise. Standard for any positive root can be written as a sum of simple roots, so that when you take this partial sum, that must be a root. Okay, that's simple. So you read it from left to right or right to left, doesn't matter. Each step you will be getting root. Okay, how do you prove this? This is the most fundamental thing. Then you can use height argument to get this correct. So if alpha is positive root, which is not a simple root, then we want to say that it must be actually, you can subtract some simple root from that support. Okay. Okay, so first thing to assume, so here is a proof. So you write alpha as summation Ci alpha I. So then you know that alpha must be positive. But if you rewrite this alpha, then this is going to be summation Ci alpha I. And this being positive, so that tells you that all the terms that appear here, all of them cannot be non-negative. Okay, so there exists I such that alpha must be positive. Okay, if all of them are negative, then the because the Ci's being okay, all this Ci's comes from Z plus. Okay, non-negative integers. So that makes it that alpha must be positive. So if alpha positive, then what will happen to the reflection? Okay, the reflection, what it does, so you take this S alpha I, apply it on alpha. So it will give you alpha minus alpha I. Look at this number. This number is positive. So you are subtracting something. So alpha minus some positive number times alpha is actually a root. Okay, so if you take the string, okay, like you take alpha and you start subtracting. So you are reaching alpha sun times k alpha I. So this is a root, but the root string is unbroken. So because the root string is unbroken, to reach this alpha minus k alpha I, you have to successfully actually subtract. There is no other option. You have to go like this to reach this. So that means all these things should be root. So this should be root. And note that this is in phi plus, so this must be in phi plus. So that tells you that you can always subtract some root from given alpha. To begin with alpha equal to alpha I, then yeah, you can't do this actually. Okay, how it helps? So this actually helps to prove that you have this nice generators called Chevrolet generators for the simple Lie algebra or semi-simple Lie algebra. So for all purposes, you can just assume G to be simple because any semi-simple Lie algebra is direct sum of simple Lie algebras. So you can decide what you want to work with. Okay. So what we do, like we establish this Chevrolet generators now. We already fixed this H1, etc., HL. So this actually, if you think about it, span H. Okay. So now we want the generators for the positive part. Okay, let's actually take the positive part. So the positive part is actually direct sum of G alpha, alpha in phi plus. So I use this notation that actually Humphreys uses. This you should read it as direct sum. Okay, so yeah, I want some generators for n plus. What I will do, like to take this xi's. So these are all just x alpha I. I read from. Okay. So this you know that we have already fixed x alpha for the alpha of the root space, and similarly y alpha we fixed for minus alpha of the root space, and the bracket of x alpha y alpha is nothing but h alpha. So that is already there. So those things we are taking here, and then we will climb that. So this x1 etc. xl this generate n plus. And the parallel story will be y1 etc. yl will generate n minus. So where this ya is just y y alpha. Okay. Okay, let's see how to prove this. So it's enough to prove it for only positive roots. The negative roots similarly follows. So you start with a positive root, and then you need to show that this G alpha is indeed in the subalgebra generated by this x1 etc. itself. Okay. So for that we will use induction on the height, and then we just proceed. So note that we already know the dimension of G alpha is 1. So it is enough to say x alpha is in the subalgebra generated by x1 etc. itself. So if I take alpha, you know that alpha minus alpha I is positive root for some alpha I in pi. So now what will happen? So you call this as beta, alpha minus alpha. Then you can see that alpha is nothing but alpha I plus beta. So now by induction, you assume that x beta is in the is here. Okay, or you can actually somewhat stronger induction you can do. You can assume that this x beta is of the form some xi1 bracket etc. bracket xi r minus 1 xi. So this is by induction. So you can just assume this to be case. So then if you take x alpha, you know that
the bracket x alpha I, x beta must be non-zero and it must be element of your space. Okay. So yeah, maybe like let's not worry about let's worry about only the non-zero elements in the G alpha, because I don't want to write x alpha as it is. But anyway, so let me rewrite this. So you are writing alpha as alpha plus beta. So by induction, G beta is subset of this x1, etc. xl. Not only that, if I choose any non-zero element here, any non-zero element, I can assume that this is of the form some xi1, etc. xi or minus 1 xi. But then, so you choose, say, power x alpha, g alpha. So then x alpha will become x alpha I is x for some. So that takes you apply induction. Okay. So then it becomes clear that this x alpha is inside this subalgebra generator. X1, etc. So because see the x alphas I already chosen. Okay, I don't want to like use that because the structure constant may vary. Okay? When I take successive bracket, I may not reach x alpha, but it's enough to reach some non-constant multiple of x alpha. That is enough. That is non-zero multiple of x. So that is what, like, for some x alpha or x power alpha in G alpha, if you do that enough. Okay, this is just simple induction on the height that actually tells you that whatever root element that you have can be obtained from using the successive brackets of this x's. Okay, so if you think about it, you have n plus, and you have shown that this is exactly subalgebra generated. Similarly, n minus, which is also subalgebra generated by this, and then h is it's indeed the span of this. Okay, it's not even like subalgebra generated. This is being abelian, so same as this. Okay, so this is abelian. So this is also same as saying subalgebra generated. So now we use these trivial generators to write down percentage. Okay, so this is what called Chevalier generators. You take this hi, xi, and then y. So these three are generators. But note that, like we did it in the SL2 case, one can drop this to generate the Lie algebra. Okay, but it's good to keep that. Okay, because when things becomes somewhat more convenient to write. Okay, otherwise you have to mention every time what is hi, or you declare that in the beginning. So it's a simple exercise. Prove that G is generated by xi. Because the bracket xi yi is exactly h. together. Okay, so now let's start listing the relations that we know already, and then finally we will actually write down the Serre relations. Okay, so because the G is generated by this, so we have the following obvious relations. So Hj, so H being abelian, you must be having Hj is 0 for all ij. Okay, and the second relation is that you take Hi and then apply it on Xj. Okay. So then, so let me just use the simple roots to write down the relations. So again, one can just use the Cartan, not the Cartan matrix. So recall alpha I, okay, alpha j Hi is nothing but Aij. So this is the notation. Okay. So recall H alpha j of Hi is nothing but, because Hi is nothing but 2Ti divided by alpha I. So if you think about it, this is exactly 2 times alpha I, alpha j of alpha I, so which is the inner product. So if you use the inner product, then this is twice alpha j alpha I divided by alpha I. Okay, so that is the notation. And that is the entry of ijth entry of the Cartan matrix. Okay, so but it's okay to use this roots in order to write the relation. So let's use that. So basically, you know that H acts on X alpha is given by alpha of H X alpha. So if you use that, you get here alpha j of Hi and then Xj. Okay, and this is also true for all j. And the third relation, similarly, Hiyj is nothing but minus alpha j Hi Yj. And then the fourth relation, so these things tells interaction between H part and N plus N minus part. Okay, so the way you need to actually read this, the vectors that we have written here, so these are all some kind of weight vectors. Okay, so we will start introducing this notion of weights. So the H weight of Hj is 0, the H weight of Xj is alpha j, and then the H weight of Yj is minus Fj. So that's why it's easy to write on the weights first. So now we will see how N plus and N minus interacts. Before that, we have this obvious relation X alpha, Y alpha is H alpha. So let's write down that. So Xi, Yi is nothing but Hi. Okay, if you want to write down single-handedly, so if you put J here, then what happens? So this has weight. So this has weight alpha I. This has weight minus alpha j. So if you take the bracket, then it will have weight alpha I minus alpha j. But you know that for simple roots, the difference alpha I minus alpha j never a root. Okay, so that means whenever I not equal to j, you get actually 0. But when I equal to j, you get Hi. So that means here you get the Kronecker delta Ij. So this is the Kronecker delta. It is the one when I equal to j, otherwise 0. So these relations are immediate. Okay, so this all just comes from the fact that you have root space decomposition. But then if you go a little bit further and then use SL2 theory and then understand the properties of root strings, So then we can write down some relations that actually happens inside n plus as well as n minus. Okay. So recall, so maybe it is proved during such a lecture. I don't know. But if you have it hasn't been proved, then we will do it as exercise. Okay. Suppose if I take alpha, beta be two roots. Okay. So let's take the positive root, because we are going to only use it for that. So then we want to talk about the beta string, sorry, alpha string through beta. So alpha string to beta. So that means you fix beta and then you start adding and then subtracting. And then you go all the way up to where you stop. And then you come down to all the way where you can stop. But then the result is this is unbroken. This is unbroken. That means all of them are roots. Okay. So if you consider this alpha string through beta, so beta, beta plus alpha, wherever like it stops, you stop here on the right side, you stop on the left side. But then this interval that you are considering minus p to q, it's unbroken. So what I mean by that, those I such that alpha, sorry, I alpha plus beta is in phi. So this is as a subset of minus pq. So it should be equal to minus p. So that is what the first version of this string property says. The second version is actually giving you the formula for actually computing this p and q. Okay, so the relation says beta of h alpha is exactly p minus q. Okay, so this is something you can prove using SL2 theory. So the interestingly, you can either just go through the structure theory and then prove this. Okay, like using this. Yeah, if you come from semisimple algebras using SL2 theory, you can prove this. Not a problem. But one can prove this without getting into Lie algebras. So this is actually property of root system. So if you have a root system, abstract root system that you must have seen, even in the abstract root system, you have the string property. Okay, so this number you need to interpret. This is just nothing but 2 beta alpha divided by alpha. Okay, so both proof carry some merit. Okay, so yeah, you should be comfortable. Okay, so now let's get into this relations. So what we are interested in, so we fix xj and then we keep applying xi and then see how far we can go. Okay, so note that if you want to see like where it stops, okay, so you can start with xi xj. Okay, so whenever alpha I plus alpha j is a root, then what will happen? Like so this is going to be non-zero. Okay, but then like you keep applying this add xi on xj and then see like where it actually stops. Okay, because if this is non-zero, then that would imply, okay, let's say this is I have applied r times. So then it's immediate that add xi power any s of xj is non-zero for all s less than or equal to. Okay, so you take this add xi, you keep applying, and you can't go forever because you are in the finite root system. Every time you will be adding them. Okay, what is the weight of this? So the weight of this is alpha j plus r alpha I. So you will be adding to alpha I, and then you can't go forever because everything should be root. Okay, and this is fine. So you have to stop at some. Wherever you stop, you can see that up to that it will be there. Okay, so in some sense, that is what actually the string property is all about. So if I start with, okay, yeah, x beta, and then if I keep applying add x alpha, okay, powers. So where it first stops at 0, you have to see. And then you choose the minimal or maximal thing such that this is non-zero. Then you can see that from beta, beta plus alpha, and so on, beta plus r alpha, all of them will be root. Okay. So this is some important thing to notice. Similarly, you apply this add y alpha. So the interaction between these two kind of encoded in the string property. Okay, so in some sense, we want to determine how many, what will be this R. Okay, so that you can just determine using the string property. So note that alpha j minus alpha I is not a root. Okay, so this is property of simple roots. So that means if I take alpha j, I can't subtract. So this side, nothing. So you have to go only the right side. So you have to keep adding. Okay, and then you will be reaching the q alpha I. So you only go this side. So that means q is whatever is like non-zero. Okay, it may not be 0. It's greater than or equal to 0. And then p is for sure 0. But the relationship says alpha j of alpha I check. That's not this. Hi is nothing but p minus q, so it is minus. Okay. But what is this? This is exactly aij. So that means you can go up to aij. Can't go further. Okay. And the aij is always non-negative. Okay. Alpha j, alpha I, sorry, hi is always non-negative integer. This is in minus is a plus. So that is actually an exercise. That is because that is equivalent to saying that this is not a root. So that means when I apply xi, okay, q plus 1 time, then that must be 0. So that means I take this and then apply q plus 1. So q plus 1 is 1 minus aij. So you apply 1 minus aij times. So then you get the relation. Okay, this just uses SL2 theory, and similar relation holds in the yij case as well. So you have the relations xi add xi power 1 minus aij applied on xj is xi, etc. xi, xj is 0. Similarly, so this is happening inside n plus. So you have similar relation, the n minus what? Okay, so these two are called pair relation. And you take this first some basic relations that I wrote before. Okay. So let's call it R1, R2, R3, R4. And then you have these R5, R6. Okay.
So that is maybe YJ, sir.
Sorry, this is. So now G, the theorem says, okay, G is generated by these 3L generators, HI, XI, YI, modulo the relations R12, R. Okay, so that's a theorem. So in this theorem, like you can see that only the entry alpha I, alpha j appears. Okay, nothing else appears. Okay, so alpha j hi, which is nothing but aij. So this is what there in the presentation. Okay, let me show you here. Okay, so here it appears. Then here. Okay, so that actually tells you that if the theorem is true, then given Cartan matrix, you have semisimple linear algebra whose Cartan matrix will be. Okay, so any question about the proof? Sorry, the statement. Okay, what is the most difficult part? Is proving this. So it's really like you have to use everything that you have learned about semisimple algebras. You have to go parallel. Like you just see like what happened in the entire theory of classifying semisimple algebras. So basically, like Cartan's classification, Cartan killing classification, and then how Dinkin simplified. Okay, everything you should know in order to actually achieve this. So let's recall like how you go about it. Okay, so like what is happening in the semisimple algebra. So you have G, then immediately what you want to say, you have what is called this kata. So you have a choice of kata. So that's what choice of kata. So then from here you go to the root space decomposition. So root space. Then you observe some of the things. So for example, the dimension of G alpha is 1 for all alpha. Okay. There is a very, very important object beneath all this. Okay. So you have the root system. So behind root system, you have this while group. So in some sense, giving root system, giving while groups are same data. So the while group acts off. And if you think about it, this while group is actually generated by simple reflections. That's a result, not that difficult to prove. So you can define this group, and then you can make it act on this field. But conveniently, this action is indeed, we know, like very explicitly in the sense. So you can take the simple roots, and then you can make act W on the simple roots, and then get back everything, all the roots. So this is what you use in order to prove this, okay? Because it's easy to see that the dimension of G alpha I is 1. Then from this, you can see that the dimension of G W alpha I is 1 for all W. And then from this, you can see that dimension of G alpha is 1. Okay. So, okay, the proof actually doesn't use this. When you see very first time, you use SL2 theory. Okay. But another way of seeing is this. So you can just look at it from the point of view that we already proved that this n plus is generated by x1, etc., xl. So this is the positive part. No? This is the positive part. So now it's easy to see that. Maybe I will leave it as exercise. So it's nice exercise. The n plus is indeed spanned by all right norm elements, xi1, etc., xir, xi minus 7. So where you just run over all of them inside one plane. All possible right numbers you take, the span of that will be endless. But note that H acts on n plus, because H acting on each generator as alpha. So H acts on Xi as alpha I. So this is how you should think. Okay. So the abelian algebra that they underline that the action of that is actually very, very important. So you can also just define n plus. Okay. Like for example, if you take set of all upper triangular matrices in SL. But to understand the structure of this n plus, you are going to use how Cartan acts on it. So that actually is somewhat very, very important. So if you think about it, all you are doing is you are putting some grading. Okay. So usually the graded structures are somewhat easier to understand because the underlying the parameterizing set actually kind of controls so many things. So the grading that you are assigning is grade of xi to be alpha I, and that's what you are looking. So what I mean by H acts on xi by alpha I, usually you are assigning grade of xi to be alpha. So then how H will act on this right norm lever? So on this right norm lever, it will act as derivation. So basically, the way it acts, if you call it as a weight, so then this is exactly alpha I1 plus etc. plus alpha I. Okay. So now, if you go back, you can see that okay, the only way you can get alpha I from this expression when R is 1. So that means alpha ith graded root space or the graded space will have dimension. So that is immediate. So this is immediate. Now the while group is acting on this root system, and while group actually, like any root is conjugate to simple root, and while group preserves the dimension. Okay, the dimension of G alpha is same as dimension of G W alpha. So that you use SL2 theory to prove. So then that actually implies that the dimension of this G alpha is 1. Okay, this observation is somewhat very, very important in the abstract proof. Okay, so if you want to do anything like that, okay, you are actually going back to this abstract Lie algebra, which is defined by generators and relations. So then first you need to actually establish Cartan. That is the first step. Okay, so this is the step 1. So this is the step 1. Then you need to talk about root space decomposition. Then you need to make some observation about the root spaces that you are getting. Then you need to define while group. And then after defining while group, you should observe that all the roots will be conjugate. Okay. And then using that, you make some observation about the roots. Okay. So then you conclude. So, so more or less, this is what happens. The end of the day, you will have something like this. The abstractly defined Lie algebra will have such decomposition. Okay, and then the phi will be W pi, and this is finite. And you also have dimension of G alpha is 1 for all alpha in phi. And with this information, you need to prove that G is finite dimensional. Okay, so it is enough to prove. It's enough to prove W is pi. Because W finite will imply that P is finite. Okay. And if phi is finite, then this is finite dimensional space because each space is one dimensional. So this is already finite dimensional space. So that would say that G is finite dimensional. But proving W is finite uses geometry. So there are many proofs actually. The proof that I like is the geometric proof because the W can be embedded inside the orthogonal group of there is this natural Euclidean space now. Because you are starting with this positive definite matrix, and then you have this orthogonal group, and W will be sitting there. And you can actually say that it's a bounded discrete group. Okay, so this being bounded discrete group, and that would imply that it's finite. Okay, so that's how like you prove W is finite. Okay, so so this is what happening more or less broadly. Okay, let's see like how much details we can see. So in order to actually kind of do all these things, so you define some intermediate Lie algebra, okay, between the free Lie algebra and the Lie algebra that you are interested in. So that large algebra in some sense helps us because that will have this triangular decomposition. So you can already see that having this triangular decomposition is much more important. Okay, so the root space decomposition gives you triangular decomposition, but okay, to begin with, if you can have triangular decomposition, that is actually this. If you want to prove something very strong, at least prove the weakest question, then go to the stronger version. Okay, what is that intermediate Lie algebra? So G tilde again generated by xi, yi, hi, and modulo the relations. First four relations you take. Okay, R1, then R2. Yes. R3. And then R4. Okay, so you only take these four relations and then work with that. So, like I said, like you are interested in establishing the cartan. So the cartan has obvious choice. Okay, you can take the span of Hi. So what will be the cartan? Okay, so the cartan you can take it to be the span of Hi inside this Lie algebra. But the thing is, why this is actually like L dimensional space? you have gone modulo so many relations. Okay, so it can happen that this HIs may end up having some linear relations. But if you read the relations carefully, HI should not be having any linear. So indeed, except this Hij being 0, so that makes it, this is abelian. Okay, so this is clear that the subalgebra generated by Hi, etc., H1, etc., HL is exactly the span of H. But since you are working in G tilde, there is no guarantee that you will end up again L-dimensional space. So that is the first thing you need to check. Okay, what is supposed to be? So I'm using same notation. You should not get confused. Okay, I'm working in this abstract ELG. Okay, I'm working in G tilde. I'm using same H and R. So we will not keep rewriting. Okay, I don't want to put tilde. I will. So just like be sure that where you are working. I will repeatedly use xi, yi, hi. I am not going to change any notation. But you are in G tilde. In G tilde, the problem is the subalgebra generated by H1, etc., HL can have smaller dimension than L. It can have at most L dimensional because it's span of H. So why it has L dimension? That is the first question, because you want to preserve the pattern. So for which what you do, like I already told you, like you construct large representation of this G tilde and then use that information. Okay. So idea, construct large representation of G tilde. So what will be that large representation? So that is exactly, you take the free associative algebra generated by this y1, etc., yn. So maybe like you call it something else if you want. So this is a free associative algebra generated by y1, etc. Okay. So you already know that this is actually non-commutative associative algebra. So all possible words are there. So this is a span of all possible words, y1, etc., yr. Okay, where I1, etc., IR will come from 1, 2. Okay, so with the repetition. So once you construct, then you can see that so you want this yi at yr left motivation. So where the motivation comes from for this representation. Okay, so if you go back again, read the relations. Okay, so read the relations. So here you have xj, here you have xi, yj. So in these relations, you don't have any relations among y's. Okay. So if I take yi's, there is no relation. There is no relation among y. Similarly, there is no relation among x also, x's also. Okay, but you have to fix one of them because mostly in highest rate theory you work with n minus, n plus always scales. Okay, so that is why like it's okay to work with this y's. So you take this yi's and then so okay, let me just say like this. Okay, so basically what we want to say, so inside this G tilde, okay, so you take this n minus tilde, which is subalgebra generated by this y1 etc. yl. So there is no relation among them, yi's. So that means that that is actually supposed to be free free Lie algebra generated by y1 etc. yl. So this is supposed to be, okay, let's say y1 etc. yl, which is sitting inside G theta. So this is supposed to be free Lie algebra generated by yi's. So because there is no relation among yi's, okay. That's an intuition, like we need to prove all this. But then what is the universal enveloping algebra of that? I already told you. If you have a freely algebra, the universal enveloping algebra of that is the tensor algebra. So the universal enveloping algebra of this is nothing but this thing that you have, this here. So that is why this freely algebra naturally acts on this A, because universal enveloping algebra is nothing but A. So universal enveloping algebra acts on itself by a left multiplication. So that is what we are having. So that is the representation that we are. Okay. So U of n tilde minus being A acts on A via left multiplication. So basically, if I take, if I consider this representation as rho, okay, rho of yi on this y1 etc. yr should be exactly yi times y1 etc. So this is what the left hand means. But then like G tilde will have H part as well as N minus part. So we have to say how they also act. So G tilde has H part, okay, as well as N tilde plus part. So how they act, we have to say. But note that each yi is nothing but all weight vector for H. Okay. So H again acts on yi as alpha. Okay, this is something even true in this Lie algebra. Look at this. Okay, so H acts on yj as minus alpha j. So I missed a minus. So this is a minus alpha. So that means it has to act on this product as alpha I1 plus etc. alpha IM. So that is the formula that you write. Okay, the rho of H I on y1 etc. IYR is nothing but summation alpha ik on alpha I k raised from 1 yi1. So H part is also going to act via this summation. Okay, the minus. Okay. So now the xi part, so you can just compute it using this relation that you have. Okay, because you know that xi yi must be hi. So that is there in this algebra. Huh? Look at this last relation. Xi yi must be hi. So you just compute using this. So you can see that xi yi minus yi xi is hi. So now you know how hi acts, how yi acts. So using that, you can actually inductively define how xi acts. Okay. So the formula, for example, you see in the Carter, basically uses this, nothing else. Okay, so now by kind of inductive way, you can complete that action. So that tells you that G tilde is acting on this associative algebra. But then you can use that information to prove all this HIs must be linearly independent. So you have constructed this large representation, G tilde acts on this A, and then you know how this HI acts. So note that the HI, if I take rho of HI on Yj is nothing but minus alpha j of HI Yj. Okay, so because I told the H rate of this Yj is alpha j. So now if there is some relation among this Hi, let's call it summation lambda I Hi is 0. So this is happening, let's say G tilde. Because this relation is true inside G tilde, when you apply rho, then it should be true. Then summation lambda I rho of Hi is also should be true. Is true. But then you can apply it on Yi. So like I said, okay, you can fix one vector and then keep applying. Nah? So same thing you are doing. So now if you apply it on that vector, then you get lambda I rho of Hi Yj is 0. But then what it gives? So rewrite this. So if you take this and then rewrite, so let's write it here. Summation lambda I, this part will become this minus alpha j of H. So which is nothing but minus Aij. Minus part you can forget, then it gives Aij. And then it is Yj. Yj is non-zero vector. So only the scalar part we can consider. So that will be 0. And this is true for all Ij. But A is given to be positive definite matrix, in particularly invertible. So that will force that lambda Ij. Okay, so that means you don't have any relations among this Hi inside G tilde. So now what you can do, you can identify H with H. So then this H will have dimension L. Okay, this is sits inside G tilde. So now from G tilde, you can go to G. So G is all relations we include, okay, including the Serre relations. Then, okay, before that, you need to actually see that G tilde has triangular decomposition. So you can write this as n minus tilde direct sum H tilde direct sum n plus tilde. Okay, where n plus minus tilde, they are defined as subalgebras generated by Xis and Yis respectively. Okay, and this is not very hard. So this is just a checking. Okay, this part is just a checking. So now from here, you are actually going to G by taking this extra two relations, Serre relations. But then what happens if you denote I by ideal of G tilde generated by the Serre relations R6 okay, R5, R5, R6. So those are all looking like this, Xi, etc., Xi, Xj0, and then Yi, etc., Yj, Yi, Yj is 0. But let's have a closer look at this relation. The Serre relations doesn't mix, okay? So this is just a relation among Xis. This is just a relation among Yis. So there is no mix between them. So that means this ideal that you constructed in G tilde has to split as ideals in n tilde plus and l tilde minus. Okay, so that's what happens. So this I, you can write it as I minus direct sum I plus, where I plus will be ideal generated by X add Xi power that 1 minus Aij Xj. Okay, similarly, I minus you can define. So now G tilde is nothing but n tilde minus direct sum H. Okay, H is I have used as H, and then n tilde plus Now, if you go modulo I, you get exactly n tilde minus modulo I minus direct sum h direct sum n tilde modulo I plus. But this is exactly your G. So you can call this as n minus again, this as n plus. So as before, it will be generated by the images of this y1, etc., yl. And then this also will be generated by the images of x1, etc. x. Okay, so then you will have a triangular decomposition of G. So G will be n minus direct sum h direct sum n plus. But then if you think about it, okay, so h acts on each generator of G tilde, okay, with the weights, okay. So for example, hi have weight 0, xi has weight, okay, I'm talking about h weight, alpha I, yi have weight minus alpha I. That means G tilde, because it is generated by all this set of generators, h must act on G tilde, like whatever that as weight space, okay. So G tilde becomes weight space for h. That means I'm just telling that each element of h acts diagonally on G tilde, and it is simultaneous diagonal action because h is being abelian. Okay, so same parallel thing happens. But most importantly, if you take a word that is in G tilde, you know the weight of each generator, you can easily write down the weight of each word. Because if I take word xy, the weight of this is going to be weight of x plus weight of y. So the action is always derivation. Okay. So that means this is a weight module, but the quotient of weight module is weight module. So that makes this as a weight module. Okay. So in particularly, you have this decomposition of G into root spaces. So you can write it as h direct sum n plus direct sum n minus, but n plus you can write it as direct sum of G alpha. Alpha now come from only the positive side of alpha, because as before you just define it to be non-negative linear combinations of alpha. Okay, so you need to know what is phi alpha. So phi alpha defined, phi plus is defined to be, so those alpha comes from what is called Q plus, such that the G alpha is non-zero. So that is that you take it as definition. Q plus is nothing but Z plus span of all this alpha is. Okay. So similarly, you will have minus here. So then you have root space decomposition. So then the way you proceed, it's easy to see that because the alpha I space actually will have dimension 1 inside G tilde itself, because G tilde is the alpha I space has to lie inside n plus tilde pair, where it will have dimension 1. So it will be immediate that the dimension of G plus or minus alpha I is. But then you have to actually define the while group. Okay. So you have defined the root system. Root system is nothing but those alpha in Q, which is Z span of alpha I. So Z span of alpha I. So then you take G alpha to be non-zero as before. So now, what is the while group? So you have to see that this add of xi and then add of yi, they act locally nilpotently. So this is something like you can't say nilpotent because you are not working in the finite dimensional space. We need to prove that. Okay. So that is why you can check it is locally nilpotent action. But once you know that it is locally nilpotent action, then as before that you must have seen in semi-simple algebras case, you can immediately define these exponential maps. Okay. So using the exponentials, you can easily define what is called theta I. So the theta I you define to be exponential of add xi composition exponential of add minus yi composition exponential of add xi. So this is something you must have seen in actually semi-simple algebra case. For example, like if you are interested in going from your Lie algebra to either algebraic group or the while group, you need to use this exponential. Okay. So if you take add x being nilpotent, okay. So then exponential of add x, the subgroup generated by that is the algebraic group that you are interested in. So now inside that, if you are interested in this while group, then you have to take this particular exponential. So this is exactly acts as SI when you restrict to the cartan. So theta I restricted to the cartan is SI. So this is something like motivated again from the semi-simple algebra theory, and this is not hard to check. This is very easy to check. So then, so what is SI? So that is the question. Okay, that SI is now given using the cartan matrix. Okay, SI of Hj you define to be the operator. It is Hj minus Aj Hm. You can simply define this thing. Okay, no issue. See, we are starting with the cartan matrix, and then we have this abstract simple roots alpha I. And then we have this numbers alpha j of alpha I. Okay. Other than that, we don't know anything. So you have to define this SIs. But these SIs, you can easily prove that they are all invertible, and these SIs lie inside GL of H. But you know that this is this is being finite dimensional. So this is some group inside this set of invertible operators. But that actually gives you definition of the while group, but there is no guarantee that, okay, still there is no guarantee that this while group is fine. But then these numbers, they are coming from actually this cartan matrix. So they define inner product on this H as before, and that makes this whatever the real span of this alpha I to be. So like what you do there, okay, the real span of alpha i's, so that actually will be Euclidean space. So you have this AJ, now you can define it on the generators and then extend, not a problem. So once you have this Euclidean space, you can think this SI inside that Euclidean space, okay, this Euclidean space. So, but these SIs are all like, it's easy to see their involutions, okay, and distance preserving, same story goes through. So they are orthogonal transformations. So these SIs will lie inside the orthogonal transformations. But then to prove that it is actually finite, it's enough to prove it is actually has it is bounded inside this orthogonal group discrete. Okay. So that is actually something like yeah, one has to check. Anyway, I'm running out of time, so I don't think I will be able to do all those things. But this is the story that actually proceeds. Okay, but then still you need to prove something more. So from here, once you define this while group, you need to prove that the phi that you defined abstractly is obtained from all possible W conjugations of simple roots. Okay, so from here, you need to again use some SL2 theory, same as before. The SL2 theory proof actually kind of goes through here. So using that, you can prove that dimension of G alpha will be same as dimension of G W alpha for all W. Okay, so you need to prove it for only one generator SI, and for which you use that SL2 copy of defined for that SI. So these things kind of goes through like without any difficulties for infinite dimensional. Okay, this Aij could be any matrix as long as you get SL2 triple, then these, for example, this fact actually goes through. But where problem comes, like when you look at this, it's not a problem. It's a new thing pops up when the Cartan matrix is not positive definite. Then you end up getting actually infinite while group. Okay, the infinite while group actually tells you that your root system is infinite dimensional. The root system is infinite, so the Lie algebra is infinite dimensional. Okay, this is the rough picture. So if you are very much comfortable with SL2 and the theory of root system, the rest of the proof actually kind of not that hard to actually prove. And final thing is, it's easy to prove it is semi-simple, okay, because simple. So once you have the root space decomposition, then it is just as before, like in SLN, for example, how you prove it is simple. Huh? So same way you can actually prove, or you can actually just use the information about the root system to prove that this must be semi-simple algebra. And the roots are, suppose root system is irreducible, then you will be ending up getting simple algebra. So that is actually kind of not hard, because once you establish all these things and you know that the Lie algebra has this root space decomposition, then it's a simple exercise that it is actually semi-simple algebra. Okay, I will stop here. So we can actually meet during the tutorial. And then maybe you can ask some questions later.
Yes. Any quick questions? Okay, so in that case, let's thank Professor Venkatesh for making these difficult proofs simple. And I hope that you will continue for the last tutorial of his. I have also shared the feedback form in the chat as well as I have sent it in the email. Please fill that up. It's very useful for all the speakers to get feedback. And thanks, Venkatesh.
Yeah, thanks.
We'll meet again at 11:30 in 20 minutes.
Sure.
Shall we start? Shall we stop recording?
Yes, please.
Okay.
Yes.